So we're going to talk about another type of integral where we can use u-substitution. And this is when we have exponential expressions as the integrand or logarithmic expressions as the integrand. Okay, so the main rule that we know and that we always try to use, and we've used in all of our previous videos, is our power rule for integration. And what that says is the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. But when we learned that rule, when we started integrating, we said, well, hey, n is not allowed to equal -1. Because what we know, remember, the derivative with respect to x of natural log of x is 1 over x. So that would then mean the integral of 1 over x, which is the same as the integral of x to the -1, that would equal the natural log of x plus c. Okay, so we have a rule for integrals with logarithms involved and also a rule for integrals with exponentials, two new rules. So I'll just come over here and write my addendum. We say that n cannot equal -1. So this gives us a new rule. What we can say is the integral of 1 over x dx, which is equal to writing x to the -1 dx, that is going to equal the natural log of the absolute value of x plus c. Okay, so this is something we want to know and be able to use. And you may say, Ms. Stein, why are there absolute value bars in here? And the reason that is you can't take the log of a negative number, and we don't know what x is, right? So that argument, whatever this x is that ends up in the argument, we have to say, well, x has to be a positive value. Otherwise, this doesn't work. So we always throw absolute value bars in there when we have a variable as the argument. So let's do an example where we might use this rule. And we often see this rule used when we have, when we're integrating something that is a rational integrand, a rational expression in there. So in this case, we have the integral of 10x over 5x squared plus 7 dx. So when we are trying to decide how to choose my u value, one of the ways or methods that we said we would do this would be to choose what is in the denominator. And it's not always that way. These are just general rules. So in this case, I'm going to say, let u equal 5x squared plus 7. That means then the derivative of u with respect to x is 10x, or rather du equals 10x dx. And I see that 10x dx showing up right there in my problem. So in this situation, that would be the same as u in the denominator and du in the top. Or rather, the integral of 1 over u du. And by our rule above, we know that that integral, that's going to be the natural log of the absolute value of u plus c. So this becomes the natural log of u plus c. So we're almost done, but we can't leave our answer in terms of u. We have to go back to x. So u in terms of x is 5x squared plus 7. So this becomes the natural log of 5x squared plus 7 plus c. And let me ask you, 5x squared plus 7, is it possible for that to be a negative number? And the answer is no. Squaring something's always going to be positive. Multiply by 5 will be positive. Add 7 will be positive. So in this specific situation, it would be okay to rewrite that as parentheses. But of course, nothing's going to be counted wrong if you leave that with the absolute value bars in there. So this is our final answer here. Let's do one more expression with an integral that will turn out to have a logarithm as the solution. So here we have another integral to evaluate. It's the integral of 3 secant squared t divided by the quantity 6 plus 3 tangent t dt. And we have options. We have to decide how to choose our u value in order to make this work. And please don't get discouraged if the first u you try doesn't work. You may need to try several options. How am I so good at it? I've had a lot of practice. So in this case, because we're dealing with a denominator, I am going to choose this to equal my u. All right, so I'm going to say let u equal 6 plus 3 tangent of t. So that means I need all of this left in the numerator. I need that to show up as my derivative. So let's look at this. The derivative of u with respect to t, derivative of 6 goes to 0. And then the derivative of tangent, that would be 3 secant squared t. So du equals 3 secant squared t dt. And this is a nice, easy to deal with substitution. So in my denominator, I have u, and in my numerator, I have du. And this is the same as writing the integral 1 over u du. Of course, we know that integral because we know our rule. So this would be the natural log of u, absolute value, because the argument must be positive, plus c. And my last step would be to plug my u value in, and u is equal to 6 plus 3 times tangent t plus c. And because tangent can give us a negative output, we need to make sure we leave those absolute value bars in our answer. All right, so we've seen that when we have rational expressions and we're taking we're finding the integral of something that's rational, a lot of the times it's going to end up with that natural log in there. So let's talk about what happens when we have exponential expression. So if we're dealing with exponential expressions, we know that dx of e to the x is e to the x. So if we think about integration, the integral of e to the x dx, what would that be equal to? That would also be equal to e to the x plus c. And this is a rule you're going to need to know how to use. Now, we also have a situation, the base is not always equal to e. In this case, our base that we were differentiating or integrating, the base was e, Euler's number. So let's do an example, and we're just going to make sure that we pay attention to this new rule for integration. For integration, exponential expression, Euler's number is the base raised to some variable power. So our first example here, we're going to evaluate the integral 2t e to the negative t squared dt. So one method that we use potentially to choose my u value we said that sometimes we can choose u by looking at the expression in the exponent. So that's what I'm going to do here. I'm going to let this piece, t squared, negative t squared, that's going to be my u. So let u equal negative t squared. And so that means the derivative of u with respect to t equals negative 2t, or rather du equals negative 2t dt. So negative du equals 2t dt. And I see that 2t dt in my original problem. So I can rewrite this integral as e to the u times negative du. That's the same as negative integral of e to the u du. Of course, we know what the integral of e to the u du is. It's e to the u plus c. So this becomes negative e to the negative t squared plus c. And that's my final answer. So I'd like to show you one last example in this video, and this one can be a little bit tricky. So here we're going to integrate e to the square root of r divided by the square root of r integrated with respect to r dr. So we've got options. We might look at this and go, okay, well, this square root of r in the exponent, that could be my u. Or this denominator, square root of r, maybe that could be my u. But in this situation, we're going to do something a little different. We're going to allow the entire numerator to be u. All right, so let's look at that. One of the first things we do when we're dealing with radicals is we almost always take them and write them as 1/2 powers, or a rational power. It's a square root, so it's 1/2. So in this situation, I'm going to let my denominator, e to the r to the 1/2 power, be u. So u is equal to e to the r to the 1/2 power. So what would the derivative be? The derivative of u with respect to r, well, the derivative of e to anything is itself. So we've got e to the r to the 1/2 power. Of course, that's not just an x in the exponent. So we need to take the derivative of the exponent using the chain rule. And so the derivative, we've got ddr of r to the 1/2. We've got that multiplied by here. So the derivative of u with respect to r is e to the r to the 1/2. And the derivative of r to the 1/2, that is going to be 1/2 r subtract 1. We get negative 1/2. So let's consider what we are trying to create. We're trying to create this r to the 1/2, or 1 over r to the 1/2 dr. So let's see if I can take this and rearrange it. So I already have r to the 1/2 in the denominator. So I'll multiply here. I've got du equals e to the r to the 1/2 times 1/2 times 1 over r to the 1/2 dr, and multiplied the dr up. And these two terms, I can divide them to the other side. So dividing by 1/2 is going to give me 2 du. And dividing by e to the r to the 1/2. I'm left with 1 over r to the 1/2 dr. So all I've done is some algebraic manipulation to make this work. Pause the video and make sure you understand all of my algebra because this is a true statement. All right, so I'm running out of space here. I'm going to rewrite our integral that we were originally dealing with. We were dealing with e to the r to the 1/2 over r to the 1/2 dr. And I see what I've got going on here. I have e to the r to the 1/2, and then my over r to the 1/2 dr. And I know what those are both equal to. So using my substitution, u goes in right there, and this is going to go in for 1 over r to the 1/2 dr. So this becomes the integral of u times 2 over e to the r to the 1/2 du. And again, this is a good time for you to pause and make sure that all of this makes sense. All right, so we are just looking at this piece now. This is what we have changed it into. And what you might notice is that I again have an e to the r to the 1/2. And e to the r to the 1/2, that's equal to u. So I can say, well, this is, I still had my u, times 2 over something du. And we said that that something in the denominator is u. Now, if I look at simplifying this, my integral is 2 du. And that is very easy for me to integrate. When I integrate that, I get 2u plus c. And plugging my u value back in, that is 2. Remember, u is e to the r to the 1/2 plus c. Or rather, 2e to the square root of r plus c. And so this is my final answer for this. You can check that using the derivative. If I take the derivative of this answer I've drawn in the box here, it should give me exactly what I started with. So we've seen 2 examples integrating where we get a logarithm as our solution, and 2 examples integrating with Euler's number, an exponential expression, e to some variable exponent.